Before we get into this video, I have a huge favour to ask. The goal of this channel is to make high quality educational videos on electronics topics which may be of interest to viewers. These videos take a lot of effort to produce, including design, research, scripting, execution, multi-camera video recording, and editing. If you like the way I cover these detailed electronic circuit designs and analyses, please consider subscribing to the channel and clicking on the like icon. This signals to the YouTube algorithm that you found the video interesting or useful and will encourage it to invite more like-minded people to view it. In return, I'll endeavour to bring more interesting electronics topics and projects to you. Thank you. In my last video, we took a deep dive into exploring the 555 timer and trying to perfect a 1:1 mark to space ratio from the pulse output from pin 3. And we arrived at this circuit here. So we have two resistors in the charging path going through this diode and charging up this capacitor, and two resistors and this diode in the discharging path through the discharge pin 7 of the 555. Now we looked at these two resistors here, which are variable resistors, and they are ganged together. So these will keep pace with each other as you turn the variable resistor. So these help determine the frequency. And this resistor and this resistor, these are RA and RB, they are fixed resistors and they set the minimum frequency and period. So these resistors are fixed and these two are variable. So in today's video, I thought we would look at an interesting idea of, well, we've previously perfected a 1:1 mark to space ratio, and what I thought we'd do in this video is explore to see if we could actually change the mark to space ratio but have a smaller mark and a longer space, and if so, how far could we control it? Now, deriving from that, from this diagram here, what if we remove the ganging of these two variable resistors together, and we took that off, and we controlled this resistor, this variable resistor, and this variable resistor independently of each other? That would mean that we could then have a charging time constant going this way to charge the capacitor, and a discharge time constant going this way to charge through this resistor, and then through this diode. So that would mean that this would control the mark time, and this would control the space time. Now, the interesting thing about this is that this also changes the theoretical formulas which we looked at previously, which were, let's see, which were over here, where we had the time for TH being given by this formula and the time given for the space being given by this formula here. So the formulas actually change when we have this circuit configuration, and they change to this. Let me just get these off here. And they change to TH being equal to 0.693 times RA1 plus RA2 times C1, and TL is given by 0.693 of RB1 plus RB2 ganged together, joined together, added together, times C1. So TH and TL have the same time constant formula for calculating the period that the mark and the space are each independently calculated for. Now, I've chosen some resistor values. RA1 is 100 kiloohms and RB1 is 100 kiloohms, and RA2, the variable resistor, the preset variable resistor, RA2 is going to be 1 mega ohm, and RB2 is also going to be 1 mega ohm. And the capacitor is 10 nanofarads. So we're going to do our calculations based on these numbers first, and then we're going to actually work out what the time constants are for the mark to space values for those. We're then going to use those resistors in the real circuit, and we're going to actually take measurements on the oscilloscope, and then we will compare the two. So I've drawn a little table and I've plugged in the values. So with RA equal to 100 kiloohms and RB equal to 100 kiloohms, plugged into that formula, we get a time constant for TH of 0.693 milliseconds. And similarly, the time for TL is also 0.693 milliseconds. Now, if we keep RA as 100 kiloohms, but then we wind up the potentiometer, the preset variable resistor, on RB to its full 1 mega ohm value, then RB will be 1.1 mega ohms, because 1 mega ohm plus 100 kiloohms is 1.1 mega ohms. So with these two values, we will see that TH is still 0.693 milliseconds, as it was previously, but TL is now going to work out to be 7.623 milliseconds. So it's much, much bigger now. So remember, this is due to the capacitor being discharged through this path here. That is RB, RB1 and RB2, which combined make RB. There's RB, 1.1 mega ohms now. So that's 1 meg and that's 100 kiloohms. So 1 meg and 100 kiloohms is 1.1 mega ohms. And so that 1.1 mega ohms is the discharge time constant for this part of the circuit for discharging. And that's what determines TL over here. Similarly, RA, if you wind up the variable resistor, the preset variable resistor RA, that's this preset variable resistor, to its full maximum value, then this will be 1 mega ohm. Added to this 100 kilo ohms gives you 1.1 mega ohms. And so the charging time is through there, 1.1 mega ohms through there, through this diode, and then to this capacitor here. So that's this part here. So that gives us a charging time for TH of, like before, 7.623 milliseconds. And with RB equal to 100 kiloohms, like before, you've got a low time of 0.693 milliseconds. And lastly, the final extreme is when both of those preset variable resistors are both set to 1 mega ohm each. And so you've got a charging time of 7.6 milliseconds, 7.623 milliseconds charging, and 7.623 milliseconds discharging. So that's what we have in this table here. So those are the theoretical calculations. And what we're going to do now is we're going to switch to the live circuit with these components in place, and we're going to actually record the values that we measure on the oscilloscope. Right, okay. And I've labelled the two preset resistors here. So this is RA2 and this is RB2. So RA is the preset resistor here, and if we follow these lines across here, this yellow wire comes to this 100 kilo ohm resistor here. So these two resistors are the charging part of the circuit. They control the mark, And then this 1 mega ohm resistor comes around to here, connects to this 100 kilo ohm resistor over here, and then connects to the junction of those two diodes. And so that is RB. So those two components there are RB combined. So this is RB2, and these form the discharge part of the cycle. So that's TL. Okay, so looking at the oscilloscope, we can see we've got a waveform, and we can control the X position like this, and we can control the Y position like this. So I'm just going to mark it up like that. That's fine. And now looking at this circuit, we've got RA2, and if I adjust RA2, remember this will control the mark. So looking at the oscilloscope, just watch this line here. That's the mark. So here we go. I'm going to adjust it. And just watch that line. You can see only the mark moves. Okay, the space value stays the same. The mark value adjusts. So that's the minimum and that's the maximum. So that's with the resistor at 0 ohms, and that's with the resistor at 1 mega ohm. So with this resistor at 0 ohms, only the 100 kilo ohm resistor is in circuit. At this point here, with the resistor turned fully anti-clockwise at maximum, that's now at 1.1 mega ohms for RA. So you can see here we're adjusting the mark. And by the way, you can see by adjusting it this way, we've got a value of a mark which is less than 1, a mark to space ratio which is less than 1. And we're going to calculate that as well. Now, having just adjusted the mark value like this, I'm going to leave it somewhere in the middle for the moment. And I'm now going to adjust RB2, the discharge. And now watch the space value. That's this mark value here, this length here on the lower line. So as I adjust that, you'll see that gets longer and shorter. There we are. So that's the effect that RB2 has on the circuit. It controls the space-time, TL. So now we're going to take values for all of these components, all these positions of these variable resistors, and we're going to write them down. So with A2 set to minimum, and RB2 set to minimum, we can see here, if we adjust the time base, we bring that forward like this, we can see that we have, adjust the position there, just adjust it a little bit off there like that. There we go, that's perfect, I think. There we go. We actually have 4 squares for the mark times 0.2 milliseconds per division. So that comes out to 0.8 milliseconds. Now for the space, TL, if I just adjust that very slightly and bring that up on here on the graphicule. Well, just trying to make sure that we've got this right. It looks, well, it should be 4 squares as well. I'm going to give that. It should be 4 squares. It's around about 3.9, just across there. 1, 2, 3, 4, roughly. It's about 3.9, but it's about 4. And again, that's 4 times 0.2, so that's 0.8 milliseconds. So we'll write those values down. Let's bring the book back in. So TH was 0.8 milliseconds and TL was 0.8 milliseconds as well. Okay, so the next thing we're going to do is we're going to wind up RB to the maximum value of 1 mega ohm to give us a total of 1.1 mega ohms for that branch there. So RB we're going to wind up to 1 mega ohm. So we are now going to wind up RB here to its maximum value. And we're going to watch what happens on the scope. Whoa, it went off the end there. So can you see that? So I'm going to wind up the time base a couple of notches like that. We'll just adjust the X position like that a little bit. And we will wind this right up to maximum and see what happens. There we are. You can see the mark stays the same. The mark does not adjust, but the space does. In fact, it's gone so far over, we have to notch this up to 2 milliseconds per division. So let's just go through that one more time. This is at RB minimum, and this is at RB maximum. I can't even say it. RB maximum. So RB maximum we can see is 2 milliseconds per division on the time base, and we can see here that we have a mark of, well, it looks like it's very, very difficult to tell, but we can just adjust this. We're going to have a look at the mark first. We're going to have to read it on a lower time base. So I've taken this down 3 notches to 0.2 milliseconds. And we can measure that mark as being, well, we know that it's going to be 4. Right, so RB is the space that we want to measure. RA we know is 0.8 milliseconds. We can see that there. And then if we look at our TL, if we look at TL, we've got this on 2 milliseconds per division now, and we can measure this. We can move X position like this, and we'll just take the reading off the center there, and we can see here on the graticule we've got 1, 2, 3, 4, 4.6, roughly 4.6. I can't get any more accurate than that. It's about 4.6 divisions times 2 milliseconds. So 4.6 times times 2 milliseconds is going to give us 4.6 times 2 is 9.2 milliseconds. So let's write that down. So we had 4.6 squares times 2 milliseconds. So that's 9.2 milliseconds for TL. And we had 0.8 milliseconds here for TH. So that remained unchanged because it was in the RA branch. So that didn't change. Now we're going to repeat with moving RA to 1.1 mega ohms and RB back down to 100 kilo ohms. So now we're going to adjust RB back down to 100 kilo ohms. So the space gets shorter. And we're going to adjust RA2 up to 1.1 mega ohms. Here we go. There we are. All the way up to the top. There we are. So that's now at 1.1 mega ohms, or rather RA2, the variable resistor, the preset variable resistor, is at 1 mega ohm plus the 100 kilo ohms over here, makes the total for that branch, for the charging branch, 1.1 mega ohms. So now if we look on the scope screen, we can see that we are on 2 milliseconds per division, and we can measure the number of squares is 1, 2, 3, 4 squares, exactly 4 squares, times 2 milliseconds, so that's 8 milliseconds for the mark. And the space we can measure by clicking this over here. This is harder to measure because there's so little of it. but it is about 0.8 times 1 millisecond. So let's write those down. So the mark was 8 milliseconds, 8.0 milliseconds, and the space is 0.8. 0.8 milliseconds. And that's consistent with what we had here earlier. TL, when the resistor is at 100 kiloohms for RB, we had 0.693 milliseconds here, and here we're getting 0.8 milliseconds here for both of these two here, where you've got 100 kiloohms for RB both times. So that's consistent, and that's consistent. So, sorry, so that's consistent. Those two there are consistent. So now we've got one more measurement to take, and that is when we wind both resistors, both variable resistors, up to 1 mega ohm to give us 1.1 mega ohm in total for each of those branches. So let's do that quickly now. Bring the circuit back into view. And we are still on there. We are on a time base of 1 millisecond per division. And we are going to wind this one fully clockwise. Fully anti-clockwise. And there we go. Oh, we can't see it because we're on a poor time basis. Let me just adjust the time base here. Right, so I'll now wind this fully like this, and you can see the space is getting bigger and bigger and bigger until we get to about there. And this one is fully anti-clockwise as well. That's right, there we are. So this is now with RA2 1 mega ohm and RB2 1 mega ohm. So both of these with their 100 kilo ohm series resistors are 1.1 mega ohms each. Sorry, did I say one? Yeah, so this is 1 mega ohm, 1 mega ohm, and these are 100 kilo ohms each. So they're, the two branches are 1.1 mega ohm and 1.1 mega ohm. So RA is 1.1 mega ohm and RB is 1.1 mega ohm. So for TH, we have 4 squares times 2 milliseconds. So that's 8 milliseconds. And then for TL, just putting that on the graticule, we can see we've got 1, 2, 3, 4. It's about 4.6. And the scope is jumping about a bit, but it's about 4.6 squares. So that's 9.2 milliseconds. So let's put that on the table here. So that is 4 times 2, that's 8 milliseconds there. And this one here is 4.6, that's 9.2 milliseconds. And that's consistent with what we had before up here. So these are our values that we have measured, and these are the values that we previously calculated. So it's now a question of going through these and correlating them to see how close they are to each other. So now we've taken our measurements and we can compare them with the theoretical values we calculated earlier. And we can see that we calculated theoretically that the smallest TH is 0.693 milliseconds, whereas we actually measured 0.8 milliseconds. And for when the resistors are at their maximum values, we calculated 7.623 milliseconds, and we actually measured 8 milliseconds. And perhaps for the TL here, we can see we actually measured 9.2 milliseconds. So this is quite a bit of a rogue value. It's quite a bit different from the 8 milliseconds we were expecting. If the two branches were exactly the same, they should have produced exactly the same result of being roughly 8 milliseconds. but a whole 1.2 milliseconds difference is quite a big difference. So there must be a rational explanation for that. So let's just take a look at the resistor values in the circuit. So here we seem to have a problem with one of these resistors. In fact, we might have problems with both of them. So let's have a look at the actual resistor values when we measure them with a meter. So I'm going to bring in my meter into view here. Can we see that? We can see that. There we are. I'll switch that on to ohms. Bring in a couple of leads. And we'll take the first resistor, which is RA2, and we can see it connects to here and then to positive. So if I take it out of positive here, then in effect removes it from the circuit. In fact, the other lead has also popped out. That doesn't matter, we can put that back in later. So we'll just take them completely out of circuit and we'll measure across here, and we'll measure this value here and see what it is. So in practice, the actual value of the variable resistor RA2 is 954 kilo ohms. So it's not quite 1 mega ohm, it's about 46 kilo ohms short. So just write that down. So it's RA2. (954 kilo ohms). Now if we measure the other resistor, RB2, so I'm just going to pull this lead out from here and the other lead out from here, and we'll measure across there. And we can see that the actual value of the resistor, fully wound up, should be 1 mega ohm, but it's actually reading 1.135 mega ohms. So it's 135 kilo ohms over. That's a massive amount, because the limiting resistor over here in series with this variable resistor is 100 kilo ohms on its own, and this has got an overreach on its own value of 135 kilo ohms, which is more than that. So in fact we actually have 1.235 mega ohms in the circuit here when we were expecting 1.1 mega ohms. So these are adding a massive amount of error to the difference between what we calculated and what we actually measured. So let's write that down as well. So RB2 measured was 1.135 mega ohms. That's a lot. So we found that these two components are quite a ways off their intended 1 mega ohm values. One is a little bit under, about 5% under, and the other one is about 13% over. And so what we'd really have to do is do all the calculations all over again, knowing those new values, and then that might tighten up the differences between the calculated values for TH and TL and the measured values for TH and TL. Which brings us onto another idea that we need to consider, which are the sources of error. So we have got, which we've just measured, we've got errors in the resistor. I can't even write these days. Errors in resistor values, because they are poorly manufactured. So these are manufacturing tolerances. And secondly, you may have noticed how difficult it was for me to read the graticule, that is the small measurements, the small markers on the screen of the oscilloscope. Now, if you think about it, you've got 1 centimeter squares, and then along the center line, the crosshairs on the center of the scope, you've got little markings, which are 5 little markings per square. So they represent 0.2 of a centimeter. And what I was trying to do was measure a whole cycle across, spread one cycle across 10 centimeters. And if I've got a 0.2 centimeter margin of error, then that means it's 0.2, that's 0.2 over 10 times 100%. So that's equal to a 2% margin of error in reading the graticule. So that introduces further errors. So you can see how all these errors are cumulative. They all add up and contribute to the differences between the calculated values and the measured values. But the significant thing we found was that there was for some reason, this TL, this 9.2 milliseconds, when we should have got 7.6 milliseconds, that's a particularly large difference. And we can see here that it's TL, which is related to the space, which is the RB branch in the diagram. RB here, so that's the discharge, that's TL, which takes place this way around here. And so that we found is RB, and RB was the one that had the biggest error in the measured resistor value. So that's what contributed so much to the large difference between the expected calculated value of TL and the actual measured value of TL. But otherwise, there is a strong correlation. That is, they're fairly close. I mean, we're only talking about 0.1 of a millisecond. So that's 0.1 of a square on the graticule of the oscilloscope screen between the TH calculated and the TH measured. So that's not a bad correlation. It's ballpark figure. That's not too bad. And likewise, the TH for RA, the charging branch, went from 7.6 milliseconds to 8 milliseconds. That's only 0.37 something. 0.377. Yes, 0.377 of a millisecond difference. So that's pretty good. I'm quite happy with that. So you could say that there's quite a good correlation between these measured values and these calculated values. So I'm quite happy with that. Now we've got one more thing that I want to consider in this little session. and that is the duty cycle. Now, previously in the previous workshop, I incorrectly stated, let me just find it here. I incorrectly stated that the duty cycle is the mark to space ratio, and that's not quite right, and I failed to clarify what I meant by the duty cycle. So I'd like to clarify what the duty cycle is. So the duty cycle is the ratio of the mark. So if I just draw it in here again like this, it's the ratio of the mark to the overall time period. So that's TH over TH plus TL. So we've now actually got some values here, and we can work out the duty cycle for all of these positions on this circuit. So if we look at the first one here, TH over TH plus TL. Oh, again, I failed to clarify this correctly. It's the ratio of TH over TH plus TL times 100%. So let me just write this formula down so it's clear. The duty cycle is equal to TH over TH plus TL times 100%. So for the first position, where we had RA and RB being 100 kiloohms, and we got 0.8 milliseconds for TH and 0.8 milliseconds for TL, the duty cycle is 0.8 over 0.8 plus 0.8 times 100%. So that's equal to 0.8 over 1.6 times 100. So that's 50%. So the duty cycle for the first one is 50%. So I'm just going to expand this table a little bit over here. And we'll say this is the duty cycle. Like that. And we can say that's 50% there. So now we can work the remainder out. And I'll get my trusty calculator again. So for the second one, we have 0.8 over 0.8 plus 9.2 times 100. So that's 0.8 divided by brackets 0.8 plus 9.2 equals times 100. So that's a duty cycle of only 8. Now we're going to do the third one. So the duty cycle is 8 divided by brackets 8 plus 0.8 close brackets equals times 100. So that's 90.9. 90.9. And the last one is 8 divided by brackets 8 plus 9.2 close bracket equals times 100. And that comes out to 46.5, and it should have been 50, but 46.5 is not bad. 46.5. So remember, that's because of the asymmetry in this resistor here, this RB2 being so wildly out from its 1 mega ohm value. Is 135 kiloohms over what it should have been. And RA2 was slightly under as well. So though the distance between where they ought to have been contribute substantially to the error in that duty cycle, which should have been 50. But 46.5 is not too far off. It's not too bad considering. So these are the figures for the duty cycle. Lastly, we should consider the mark to space ratio. Now, the mark to space ratio is different from the duty cycle because the mark to space ratio is the ratio of TH to TL, as we did in the workshop previously. So if we look at the mark to space ratio, I'll just write down the values very quickly. I'll just put them over here. The mark to space ratio over here. And so the first one was 1. Sorry, that should be 1 to 1. Like that. We'll write it down like that. The mark to space ratio for the second one is 1 to 11.5. The mark to space ratio for the third one is 10 to 1. That's because that's really easy to see here. You can see this is 10 times as big as this. So TH is 8 milliseconds. TL is 0.8 milliseconds. So that's 10 times what that is there. So that's why it's a 10 to 1. And the last one should have been 1 to 1, but it actually turns out to be 1 in 1.15. Yeah, okay. So there we are. So those are the mark to space ratio values there on this side here. So yeah, I could have put this table, this mark to space ratio on the right hand side. I wanted to do that, but I'd drawn this table up already. But that gives you the calculated representations of this waveform coming out of the 555 timer. So that's it for this workshop. I hope you found this useful. And what it means for me, now that we've done that, is I'm actually going to build this circuit onto a piece of strip board and have it as a permanent circuit that I can then use as a reference. And I'll be able to trim these values here on the circuit board. So that's going to be coming in the next workshop. Thanks for watching, and I'll see you next time.